Hi, my name is Sagi Kedmi. I'm a security researcher at IBM Security Systems. And today I will present an attack that we developed on the Linux random number generator on Android. I will begin the talk with what motivated us to conduct this research and why we needed to attack the random number generator. We'll then have a brief, simplified overview of how the random number generator works, and I'll point out a flaw in its design. Using this knowledge, I will be able to outline our attack framework and portray two manifestations of that framework. The first one requires some local presence of the attacker on the device, and another manifestation can be employed remotely by the attacker. Finally, we'll discuss current mitigations that are used in newer devices and how some of them might not be as good as they seem. So the story is that over a year ago, we found a classic stack-based buffer overflow vulnerability in one of the most critical services in Android, the keystore service. The keystore service is responsible for storing crypto-related data, such as private RSA keys, VPN credentials, etc. We reported our findings to Google, and they fixed it in KitKat. We also published a white paper regarding this vulnerability, and more information can be found there. In order to create a working exploit, an attacker must overcome several defense mechanisms. An alphanumeric filter, which is imposed by the keystore service, and other defense mechanisms which are imposed by the operating system. For instance, address space layout randomization, ASLR, data execution prevention, DEP or DEP, and stack canaries. The alphanumeric filter and the DEP defense mechanisms can be bypassed using an alphanumeric return-oriented programming shellcode. And regarding ASLR, what we've seen is that whenever we crash the keystore service, the operating system respawns it with a new randomized address space layout. And an attacker can use this property to defeat ASLR. In our eyes, the most formidable obstacle an attacker would face when trying to exploit this vulnerability would be with overcoming the stack canary's defense mechanism. On Android, stack canaries are 4 random bytes that are used to detect stack-based buffer overflows before the execution of malicious code can occur. The enforcement of stack canaries requires a joint effort between the compiler and the operating system. On the one hand, the operating system offers 4 random bytes to a process, and on the other hand, the process's binary image must be compiled with stack protection. When the stack protector flag is used, the compiler adds code to the prologue and epilogue of each function. In the prologue, it adds code that saves a copy of the stack canary just after the saved return address. And in the epilogue, just before the code that jumps to that saved return address, it adds code that checks if the original value of the stack canary is the same as the saved copy of the stack canary. If there is a mismatch, the program will crash itself. Okay, so before Android 4.3, when the Bionic libc, which is Android's libc implementation, was loaded, it directly extracted 4 random bytes from the random number generator. On Android 4.3 and onwards, when the Bionic libc is loaded, it takes the 4 most significant bytes of something we call the AT-random. The AT-random is a pointer to 16 random bytes that each process has. The AT-random gets allocated during the process creation, and every process has it in its address space. Android's process creation model is a Unix-like process creation model, where a parent process uses the fork system call to create a child process which is identical to its parent. And then usually, please remember this, the exec system call is used to replace the child's binary image with a new one. Now, the exec system call does a lot of things, but 2 important things that it does also is that it enforces ASLR, meaning it determines the address space layout of the process. And the other thing is that it populates the auxiliary vector of the process. The auxiliary vector is a mechanism of communicating information from kernel to user space. The auxiliary vector has a pointer, which is called the AT-random, which points to 16 random bytes, which are somewhere in the process address space. So whenever the exec system call is used, 16 random bytes are extracted from the random number generator, are placed somewhere in the address space of the process, and are pointed to by the AT-random pointer. And again, on Android 4.3 and onwards, when the Bionic libc loads, it takes the 4 most significant bytes of the AT-random and places them as the canary value. Please remember this, the process creation model. We will get back to it when I'll describe one of our attack vectors. Okay, so there are some techniques that are used to overcome stack canaries. The first technique is a naive brute force attack, which is inefficient and impractical to do so on a real device. Other techniques require some special feature from the process we want to attack. For example, an information leak which reveals parts or even the whole canary value. And if you are really lucky, you could somehow override the stack guard pointer, which points to that to the canary value in the process. Unfortunately, none of these known techniques were applicable in our case. So we had to take a rather different approach. And instead of trying to alter or bypass the stack canary protection, we thought, why not to attack the source of randomness in the system, which gives us actually the random bytes of the canary value. So what we did, we reconstructed the state of the random number generator using the attack I will show today. Okay, so let's wrap up things. So we found a vulnerability in a critical service in Android. In an effort to exploit it, we had to overcome a stack canary. We were unable to do so using known techniques. Canaries are 4 random bytes that are extracted from the Linux random number generator. And initially, we aimed to find a weakness in the random number generator so we could have some intelligent guess of what the canary value may be. And instead, we end up with a full-fledged attack on the Linux random number generator on Android. Okay. So now we know why we want to attack the random number generator. Before we get to how we actually do it, a brief, simplified overview of how the random number generator actually works. So the Linux random number generator maintains 3 pools. A pool is just a buffer of bytes. The input pool, the blocking pool, and the non-blocking pool. Environmental noise, such as timings between human input events or timings between these access events, is inserted into the input pool. And an estimate of how much entropy was inserted is kept by the kernel, by the random number generator. If the random number generator is working properly, this environmental noise, which is in the input pool, would propagate into the blocking pool and the non-blocking pool. Remember that if, okay? The random number generator offers 3 output interfaces: 2 character devices, the dev-random and the dev-urandom, and 1 function, the getRandomBytes function. The dev-random character device returns random bytes regardless of the amount of entropy which is in the pool. If there is insufficient amount of entropy, it blocks until more entropy is obtained. The dev-urandom character device returns random bytes regardless of the amount of entropy which is in the pool. So the dev-urandom never blocks. The getRandomBytes function works in a similar manner to the dev-urandom character device, but it was designed to be used within the kernel. For example, recall the exec system call. It eventually extracts 16 random bytes, right? So it uses the getRandomBytes function to extract those bytes and place them somewhere in the process address space, which are pointed by the AT random. It's very important, the AT random. You'll see why. Two more things. When bytes are requested from the pools, from any pool, what really happens underneath is some kind of a feedback loop. N bytes are requested, so N bytes are extracted. Then they're hashed using the SHA-1 function, are mixed again to the pool. Then N bytes are extracted again, and another SHA-1 is performed. So essentially, the output of the random number generator is hashed twice using the SHA-1 cryptographic hash function. And another thing is that regardless of the amount of bytes requested from the random number generator, the random number generator extracts in blocks of 10 bytes and truncates if necessary. So for example, if you want 9 random bytes, it will extract 10 bytes and truncate. OK, so on the left, you see the environmental noise, which is mixed or pushed into the input pool. On top of the input pool and the non-blocking pool, what you see is a time value, which is mixed in. We call this time value the seed of the pools. When the random number module is initialized, when the kernel boots up, these time values are mixed into the pools. And on the right, you see that feedback loop that I've talked before, that I've said before. Every extraction makes some bytes get. Every extraction of random bytes results in some bytes or hashed bytes mixed back into the pool. As I've said, the kernel keeps an estimate of how much entropy there is in the pool. We call this estimate the KEC, the kernel entropy count. If the KEC exceeds the 192-bit limit, noise from the input pool is mixed into the non-blocking pool. But if there is low boot time entropy, it means that during boot time, noise from the input pool is never mixed to the non-blocking pool. And what we are left with is quite a degenerated random number generator, which only depends on the non-blocking pool, the time seed, and the order of extractions from the random number from the non-blocking pool. With that in mind, I'll just have a quick overview of the boot timeline of a regular device. So the device powers on, then the bootloader loads the kernel image into the memory, and then the kernel starts to boot. Eventually, the random number generator module is initialized. This is the place where the non-blocking pool and the input pool and the blocking pool are seeded with this time value. Then the kernel boot is finished. The kernel calls the init process, which starts the Android platform boot startup process. The other two events, yes.
Start at 0 or it's real time from some internal clock?
Real-time clock of the device. Okay. On some embedded devices, we've read at least, Henninger has an excellent article on this. Some embedded devices, the input, the seeds of the pools are 0 actually, so it's very predictable. Okay, so the next two events may occur in a different order, but it is irrelevant to our attack, their order. So the first event is the event that noise from the input pool is mixed into the non-blocking pool. And the other event is the event that the phone is ready to use. For example, you can use your WhatsApp application and start chatting. Okay, so before I get into what we actually did, how we actually contributed. So when we, before we actually started our research, we stumbled upon many papers that talked about this vulnerability, low boot time entropy vulnerability on embedded devices. But many papers only postulated that low boot time entropy can result in a practical low-cost attack. And this is where we enter. None of them actually presented this kind of attack. So our contribution is we present a practical runtime end-to-end attack on this. We also formalize the attack and give a measure of its complexity, which can be found in the white paper. And we demonstrate a proof of concept against current mobile platforms. Sorry. Okay, so a teaser. What can be achieved using our attack? We're saying that given a leak of a value extracted from the non-blocking pool, recall that the getRandomBytes function gets its random bytes from the non-blocking pool, and low boot time entropy, the state of the random number generator can be predicted or determined until external entropy is too high, until noise from the input pool is mixed into the non-blocking pool. Okay. One note, we actually, in our white paper, we describe a more intricate attack flow, which we also tackle the event where the input pool is mixed into the non-blocking pool. So if you're interested, please read the white paper. In our attack framework, we use the random number generator against itself many times. The first instance of this is what we do with the leak value. Recall that a leak is just a sequence of random bytes from the non-blocking pool. Okay, so recall, low boot time entropy degenerates the random number generator, and the output of the random number generator is hashed twice using SHA-1. SHA-1 is a cryptographic hash function, and cryptographic hash functions are designed to be collision resistant, meaning that if you run a cryptographic hash function on two different inputs, it is improbable that the output will be the same. Using that, it is highly unlikely that random number generators or non-blocking pools that are seeded with different seeds will result in the same output, regardless of the order of extractions. So the immediate result of this is that every leak, which is just a sequence of random bytes from the non-blocking pool, is almost certainly the offspring of one specific seed. With that in mind, we can now describe the full attack framework. We're saying that given a leak from the non-blocking pool of a real random number generator, for example, a victim device, we could simulate many, many offline random number generators with different seeds and compare extractions with an online leak. Again, due to SHA-1's collision-resistant property, if one of the simulated random number generators produces a sequence of random bytes that is the same as the leak value, we almost certainly found the seed of the victim's random number generator, of the victim's non-blocking pool. Once we have the seed of the non-blocking pool of the victim's random number generator, we can produce the same outputs of the real random number generator until noise from the input pool is mixed into the non-blocking pool. And again, in the white paper, we demonstrated a more intricate attack flow, which takes the event where noise from the input pool is mixed into the non-blocking pool. If you're interested, read it. Okay, so you've seen the attack framework. We actually faced several problems with it. The non-blocking pool seed is 8 bytes long. And say we consider only the nanosecond part, which is only 4 bytes, and assuming that the nanoseconds are uniformly distributed, we have 30 bit of entropy, or over 1 billion different seed values. So essentially, we need to simulate over 1 billion different random number generators and compare the extractions.
This can be done offline.
Yeah, of course. This can be done offline with cloud servers or, I don't know, some government agency computation power. But we wanted to make a practical low-cost attack on this. As we will see, an offline study of a device reveals that the actual entropy is less, but this is only a teaser. We'll get to it. Another problem that we faced is that there is some kind of a hidden entropy source, which is concurrency. The developers of the random number module didn't put a lock on the extract and mix operations of the random number generator. So essentially, if two threads request random bytes concurrently, the state or the contents of the pool may change anywhere in the middle of the hash computation. So this is bad. But again, as another teaser, we will see that there is some bias in the concurrency that we can make use of. Another two problems is what can actually be attacked. We need some early boot service or that uses randomness, because remember that given a seed, we simulate a random pools that are generated by the victim's random number generator. And another problem is where can we get the leak value? So to make things simpler, we segmented or divided the boot timeline. We've seen that concurrency takes place only when the kernel boot is finished. We call, from the time the kernel boot is finished and onwards, we call this concurrency hell. Another segment is from the time the random number generator module is initialized to the time the kernel finished boot. We call this the best leak target segment. Why? Because then we don't need to take into consideration the concurrency hell or noise from the input pool being mixed into the non-blocking pool. Another segment is what we call the good leak target segment, which is from the time the platform starts to boot and the time the noise from the input pool is mixed into the non-blocking pool. And the last segment is what we call the bad leak target segment, which occurs from the time the input pool is mixed into the non-blocking pool and onwards. Again, this we also made an attack that takes this into consideration. So only for the attack I present here, this is a bad leak target. The random number generator is still vulnerable using leaks and targets from the bad leak target segment. Another two things. So leaks or attack targets from the best leak target segment, we call them a kernel boot time leak or a kernel boot time attack target. And leaks or targets from the good leak target segment, we call a platform boot time leak or a platform boot time attack target. Okay, with that in mind, we can now, we have the theory behind our attack framework. We now see how we can actually use it. So we'll have some malware, which the malware has no root exploit, don't worry. And from that malware, we'll see how we derive the non-blocking pool seed of the random number generator of some victim device. And from that seed, we'll see how we reconstruct the key store's canary value. Okay, so just a disclaimer, we have nothing against Samsung. We love them. We just happen to have a device of them. Okay, good. So we took our device and we went into the Samsung website and downloaded the kernel. We then excessively used the printk command. The printk command is used by kernel developers to debug the kernel. And output from the printk command is pushed into the kernel ring buffer. So in order to find some bias in the seed value, we put printks on the input and the non-blocking pool seeds. In order to find relevant attack leaks or attack targets, we put printk commands on the get random bytes function. In order to catch some bias in the concurrency, we fixed the seeds. Some of the experiments, we fixed the seeds and we traced the concurrency order of extraction. We traced the order of extractions from the non-blocking pool. So in total, we rebooted the device more than 2,000 times. Each time we dumped the kernel ring buffer to a file. So imagine hearing this thing over 2,000 times. It haunted us, and everyone in the office hated us. Okay, yeah. Yeah, well, after 2,000 samples, we actually realized that we have the kernel. We can just put a comment on this thing, but we didn't do it. Okay. So we haunted with this, we continued our work. And what we found when we analyzed the logs, we found a platform boot time leak, which can be used against a platform boot time attack target. The platform boot time leaks is from the Android's process creation model, application process creation model, which is not as the process creation model. So Android designers chose to spawn every application process by forking a master process, the Zygote process. Zygote is brought up by init, so it's during platform boot time, and is forked and execed. So you recall the exec, yeah? Exec means 16 random bytes are extracted from the random number generator, placed in the process address space, Zygote's process address space, and are pointed to by the 80 random pointer. Okay, so the Zygote process was spawned using Unix-like a traditional process creation model. But application processes, for example, your WhatsApp process, are created during the Zygote process creation model, which only forks a master process. Where is the exec system call? Recall that the exec is the one who enforces address space layout randomization and the one that assigns the 80 random. So all applications in Android has the same canary, the same 80 random, and largely the same address space layout. This is a serious vulnerability in Android. It is also a known vulnerability. And there is a great paper called From Zygote to Morula, which is from some MIT group. It is a great read, and it offers some mitigations to that problem. Read it. So again, we have the Zygote master process, and we have applications, for example, WhatsApp or contacts. The WhatsApp or contacts application, like every other application, share the same 80 random as Zygotes because the exec system call is never used. So what if we just have another process which just looks on its own 80 random? This is the only thing that our malware is doing. It looks on its own 80 random and sends it to some cloud service, which computes the seed of the victim device. Okay, so the Zygote's 80 random is our leak. It's a platform boot time leak, which means that it occurs in the concurrency health phase. We must take concurrency into consideration. An offline study of the samples revealed bias toward a specific extraction path or order of extractions from the non-blocking pool. What we've seen is that 20% of the samples had Zygote's 80 random bytes somewhere in the extraction path. This means that given a leak, given Zygote's 80 random, and assuming we try all possible 2 to the 30 possible seeds, the chance to find the seed of the random number generator is 1/5. Okay? But even more than that, our offline study revealed that the actual Shannon entropy of the entropy of the non-blocking pool seed is much less than what we estimated. We estimated it to be 30-bit. It is actually much less. It is around 24 bits. Just to give you the proportions, 30 bit of entropy means that there are over 1 billion different values of the seed of the non-blocking pool. And 24 bits means that only about 7 million different seeds we need to take into consideration. What? 16 and, yeah, round it up. Okay. Over 16 million, okay. Yes, and and even more, we also found that what you see here is a probability mass function of ranges of seeds, and we see that some seeds are more probable than others, so we can actually optimize our attack. We can optimize the process where we simulate random number generators with different seeds. We can just take from the ranges that are more probable and use them first. Okay, so now we've got the seed, and we looked at the early boot services, because most of them, all of them, use the a canary value. And given a seed, the probability of finding a canary of an early boot service is provided in this table. So as you can see, some of them, some of the early boot processes, we can actually with 100% find the canary value, but the key store is 6 in 100, 6%. So in total, given Zygote's AT-random, the probability of guessing the key store's canary value is 1 over 100, which is 1%. So imagine every 100 boots that a device performs, if we believe in probability, we can find the key store canary value. So if our malware goes viral, 1% of all devices that are infected will probably yield, we can probably guess correctly the canary value of their key store. But remember where we came from? We needed to guess 32 random bits. Just to give you how, to show you how dramatic is our reduction. This is the probability of guessing correctly 32 bits. 32 bits. So as you can see, this is a dramatic reduction. Okay, with that in mind, we now continue to the demo. Okay, so the AT-random X-filtrator is just a simple application which sends the AT-random to a cloud service, okay? So let's start. Okay, what you see here is the AT-random of the process, which is actually Zygote's AT-random. And in the IP, just a IBM cloud server. We are sending, it got into the cloud service, and we initialize many worker threads that simulate random number generators. And we hope to find the seed. Good. As you can see, we found the seed of the victim's device the non-block impulse seed of the victim's device random number generator. With that, on the left, you see the real key store canary. It was obtained using an instrumentation. Just we print K, the get random bytes function on the key store process, and we just saw the 4 most significant bytes. You can also have a peek at the key store canary value with a GDB server, which is installed on the phone.
So maybe I missed something, but the seed is the real-time clock
Yeah.
with 30 bits of accuracy.
Supposedly.
So let's assume that with 1% you manage to find a particular seed. Doesn't it imply that with a very precise clock that you are running yourself, you can know what will happen the next time it will turn on? Because you measure exactly how many nanoseconds passed since the previous time. So you can, once you have a 1% success, all the future device turn-ons can now be predicted with much higher probability.
It's a little bit yeah, entirely, you're correct. Yeah, of course. We took, in the white paper, yeah, okay. Great. So with the seed value, we got the seed value, recall, and we simulate many random number generators, and recall that we have a probability of 6%, of 6 in 100, and we find the canary value. Yeah, yeah, okay. Great. So we found the canary value, and I've shown you a probabilistic attack on this. We now turn to the second attack vector, which is which some of it is a deterministic attack on this. We use a mere ping 6 to get the non-block impulse seed of the random number generator of some device, and from that we can make some, we can attack some, we can make a IPv6 fragment injection or guessing the keystroke canary value. Okay, so again, we have nothing personal against Samsung. We just happen to have another device of them. We littered it with print keys and we fixed the seeds and again haunted with the sound. When we analyzed the logs, what we've seen is that there is a kernel boot time leak that can be used to attack a kernel boot time target. While the kernel is brought up, an IPv6 module is being initialized and extracts 4 random bytes from the random number generator. So it's a kernel boot time leak, recall. Okay? We call these random bytes rand. When we audited the kernel code of the S2 device of Android 4.1.2, we've seen that the IPv6 fragment identifier is computed by a deterministic function, f, and the function is irrelevant because we can just take it from the kernel code. What is relevant is the inputs and the outputs of this function. So the first input is the rand, which is just 4 random bytes that are extracted during kernel boot time. And another input is the IPv6 destination address of the packet. So when an IPv6 fragment is constructed, it is being sent from a sender to a receiver. So this is the address of the receiver. And the output of this deterministic function is the IPv6 fragment ID. The IPv6 destination address and the IPv6 fragment ID is our leak. Why? Because our rand was extracted during the kernel boot time, we can the kernel concurrency doesn't take place during this time. We can simulate many random number generators up to that rand value and feed it into the deterministic function f.
Not only it's deterministic, but also collision resistant, otherwise you get false alarms.
Yeah, right.
So is collision resistant?
I think it's not actually. I think that if you have the same inputs, it has some counter, and it's in the kernel, and so fragment IDs are never. I think in this kernel version, it was only incremented by 1 each time. Okay. Yep. Okay. So, but recall that the inputs of the f function is also at the IPv6 destination address. So we need some clever way of getting that address. With that in mind, a brief overview of IPv6 fragmentation and ICMPv6 echo request. So IP packets that exceeds the path MTU, the path maximum transmission unit, are divided into fragments, which are then sent and then reassembled by the receiver. Each fragment of the packet contains the same fragment ID, which is used by the receiver to identify fragments of a particular packet. Sorry. But there's a problem. IPv6 fragmentation doesn't happen very often. We need to make it happen. So ping 6 is the same utility you know of IPv4, the ping network utility, is a utility for sending an ICMPv6 echo request, which requires the target to send ICMP echo replies with the same exact data. So if we send an ICMP echo request with data larger than the path maximum transmission unit, we will actually make the receiver send a fragmented reply. With that in mind, we now describe a scenario. So we are in the Amsterdam Schiphol airport, and our attacker A comes and he installs a malicious Wi-Fi hotspot called Schiphol Free. Our victim, V, wants free internet connectivity, doesn't want to pay much money to his service provider, so he connects to this Schiphol Free SSID. Then the only thing our attacker is doing is sending a fragmented ICMPv6 echo request, which usually make the victim send a fragmented ICMP echo reply. So now the victim V computed the IPv6 fragment ID with the attacker's IPv6 source address. Recall that the attacker's source address is the victim's destination address on its echo reply. So our attacker A knows the IPv6 fragment ID and the IPv6 destination address, which is great, because now we can actually compute, we can actually turn on many simulated random number generators with different seeds and compare with the leak value. What we found on the S2 device was quite alarming. What we've seen is that the actual entropy of the non-blocking pool seed is way less than 30-bit. It's only 19 bits, which is above 500 different seed options. Correct, okay, 500,000 bit options. So again, the immensity of this, we estimated that the entropy of the nanoseconds would be 30-bit over 1 billion, okay? And then we, on the S4 device, we found that the entropy is 24 bits, which is over 16 million different seed options. And then on the S2 device, we found that the entropy of the non-blocking pool seed is way less than that, only 500,000 different seed values. So this attack can be done almost in real time. It's and we also found that there are more some of the ranges of the seeds are more probable than the others, so we can actually even optimize it further. Okay, so given the seed, what can we actually attack? We could use, we can make an IPv6 fragment injection. We can derive the exact fragment ID, which will be used for any destination address by the device. We didn't find many use cases for this. We can only maybe inject some data or some DOS attack. The other thing is that the canary value of early boot processes can be guessed also. So for instance, with the probability of 1 in 20, we can compute the key store's canary value given the seed. And other early boot services that we can guess correctly their canary value are presented in this table. Okay. Okay, so some current mitigations that are used in newer devices. So one mitigation is to save entropy across boots, which means that on shutdown, random bytes are extracted from the random number generator, are placed somewhere in the file system, and then on startup, this file is injected into the pools of the random number generator. Now, this mitigation depends on that the file system must be mounted, which means it must occur during the platform boot time. We'll get to why this is a problem. And also, an attacker could make the device shut down before the input pool is mixed into the non-blocking pool. So actually, this file may be also vulnerable to low boot time attacks. Another mitigation is trusted external entropy injection. For example, from a network service, or random.org, or Ubuntu's Pollinates service. The problem with this one is that it depends on the network stack being initialized and that and some cryptographic protocols that are available during the platform boot time. For example, it uses SSL certificate pinning. The problem with this kind of mitigation is that what they're saying actually is that there is some external entropy, and they inject it during the platform boot time. But what if we have a kernel boot time leak and the kernel boot time target? This mitigation doesn't help us. Recall that another mitigation is to initialize the seeds using a hardware random number generator. Recall that what made our attack very low cost and efficient is that the actual entropy of the seeds of the pools was very low. So, but if the full 8 bytes of the random number of the blocking of the pools of the random number generator are seeded by a true random number generator, which is provided by the hardware, unless this hardware random number generator is compromised by some government agency, we can, the entropy is increased dramatically of the seeds of the pools. So it will be very hard to conduct our attack, but it may still be feasible, but it will take a lot of time.
Not only time, but it will take also a lot of memory, because you have to keep a table of all the possible 4-byte leaks. How they correspond to
Exactly. You could think of some good rainbow table for this baby, but okay. You're the expert, okay. So another mitigation is to mix device-specific data to the pools. For example, the processor chip ID. It will make will make the life of the attacker very difficult because he needs now to guess some specific values of the device. And finally, in newer kernels, there are even more mitigations that allows for more boot time entropy on devices with low boot time entropy. We didn't get into them because it requires some a more deep overview of how the random number generator works, but you can find relevant information on them in our paper. Okay, talk wrap up. So we found that Linux-based devices with low boot time entropy may allow a practical, low-cost attack on the random number generator. The attack requires an offline study of the device and an online leak, and allows the attacker to predict the random number which is generated by the victim's random number generator. We've seen two manifestations of this attack framework, one which is probabilistic and requires some local presence on the device, and another manifestation which is a remote, which can be employed remotely, but which is deterministic, but can also, we can also guess the canary value of early boot processes with some probability. Finally, we've seen some mitigations and how some of them might not be as good as they seem to be. Thank you for listening and attending. Yes, please.
Yeah, so because these are mainly for mobile devices, so why cannot they just turn on the Bluetooth radio or something that's widespread and just sample some data, debias it with Numa and just feed it into that, right?
Yeah, of course, but recall that you need that driver of your RF to be initialized before it will be initialized after the kernel driver after the random number generator model is initialized. So in the time gap between the when the random number generator is initialized to the time the RF receiver is initialized, it may still be vulnerable.
Yeah, but it's still before you exit the user space. So as you go to late and all that kind of stuff.
So it is using leaks which are dependent on very early
Yeah.
applications.
Yeah.
Way before users.
You are right that in the S4 attack, you're right. If we have a platform boot time leak and a platform boot time attack target, then your method is correct. But as I've shown here, this is the same problem. But just that if you have a kernel boot time leak and a kernel boot time target, your method can still be bypassed.
So basically the IPv6, if this hardware module that provides the entropy loaded for the IPv6,
Exactly. But we've seen that there is some talk on the Linux kernel developers forums that they actually want to inject entropy to the pools during the bootloader time. So we'll see where it develops.
It cannot come from the outside world, only from internal sources.
Yeah, exactly.
Because during boot time, you're still not ready to talk to them.
Of course. Yes, please.
We were talking about using IPv6
Yeah.
to attack, and it's still during boot time. Because the scenario described, if someone is already connecting to a Wi-Fi, the device is probably booted up already, no?
It's much later that you are learning what is the presentation value. It was generated early, used in order to set up the device, but then the user actually found out about it long after.
But isn't that a stage at which instead the entropy gets much higher?
No, but the
Because
value,
the input process is already
the value is determined and
Yeah, exactly.
stores are
Yes, please.
What if the function that relates the IPv6 destination address and the ID becomes so computationally intensive that it's not possible for you to run many parallel generators, simulate them and get an answer?
It may affect the computation time, but what we've seen in newer kernels that the actual function is way it's not that deterministic. It depends on random bytes that are extracted on time of the fragment creation, fragment ID creation.
It will become much more computationally intensive. That it would
Of
be
course.
practical for you for the simulated random number generators to do it within the given time.
Yeah.
So the other idea that you said that saved the entropy and the file system, what I was thinking is immediately reboots, the memory is not being cleared. So if you would store the entropy in a known location of the memory, you could retrieve it from an unallocated space that you could gain.
This is a very good point. What we've seen is that on some, okay, so when the pools are defined, they are defined using the static C directive, and they are not initialized with zero. So if in memory the pages that were allocated, okay, so on some specific RAMs, the transistors are in such a way that it will always nullify or make pages data to be zero. But what we've seen is that in some devices, the RAM memory is of a kind which if it is not allocated by the random number generator, we have some noise, non-deterministic noise that we need to encounter. So on some devices, this random number generator is very unpredictable.
So if you don't refresh the RAM contents within the refresh time, then it can degrade and then it eventually reaches zero. But as long as if you think about a reboot, so if you think about a reboot, in the reboot process, the RAM is not losing any power at that point. So
Yeah.
the contents is there, it becomes unallocated in the sense that
Yeah, of course, of course. Yeah. Yes.
I have a possible improvement. Tell me if you can do it. Is there any way to access later on, a minute after the boot time, to access the exact real-time clock value? Because if you could do it, you could run outside a very precise clock, which will tell you how much time had passed since boot time until you are allowed to measure and get information. You know, on a PC, you are allowed to check what is the counter, how many nanoseconds happened since boot time. And then you can walk backwards, maybe not all the bits, depending on accuracy, but most of the bits will become known. What was the real-time clock when you booted the device?
Yes. We actually searched for this kind of thing because it will make our attack very more simpler. We didn't find any method that we can use.
the seconds you can find though.
Yeah, the seconds in a minute. Okay, the seconds we can guess because the second you can just boot the device a couple of times and just see what the second during when the pools are mixed, where the pools are seeded with the time value. Yes, please, sorry. But the same entropy each time, you mean?
You mean write to the kernel image every time you boot?
That would veer you or flash out and the checksums.
I don't understand.
I think he wants to overwrite parts of the kernel image every time you shut down.
Oh, no. Okay, no way. Okay. It may be.
Actually, yeah.
You break a lot of different mechanisms that allow the device to boot securely in the first place. So you have many more problems with
The
this.
kernel is signed and all, so.
So you have to put this data is not signed. Everybody.
Okay, so that's it. One final question, please.
Maybe you want to enter it.
Yes.
But if you have as a countermeasure, arbitrary PRNG, why don't you just, why would you still use this flow mechanism to generate new
Yeah, okay.
just pipe directly?
It's a good question. What we've seen is that current CPU manufacturers are giving an opcode for accessing the true random number generator. For example, the RDC and RD rand commands. So essentially, you could use the random number generator with just a simple, the hardware random number generator with a simple opcode. But this is not very common in today's architectures. But in the future, maybe. Okay, guys, thank you for attending.